I'll start with cryo-electron microscopy, and then we'll go to math. So what is a single particle cryo-EM? So this is a methodology in structural biology to determine three-dimensional structures of biological macromolecules at high resolution. You may have heard probably about X-ray crystallography as the most popular method for determining structures of proteins and other biological macromolecules. But as the name suggests, X-ray crystallography requires crystallization of the molecules. That is to find physical chemical conditions in which the molecules are ordered on a lattice, all of them pointing in the same direction. But there are actually many molecules that defy all attempts to crystallize them. And single particle cryo-EM offers a very general alternative because you don't need to crystallize molecules at all. All you need to do is just to freeze them in a very thin layer of ice. So at the moment of freezing, every molecule just picks some random orientation, random position within the ice layer. The ice layer is so thin that if you look at it in the vertical direction, you'd see at most one molecule. There is just no room for two molecules to be one on top of the other. And then you shoot an electron beam perpendicular to the specimen. The electron beam would go through the molecule, if there is a molecule there. And beneath, you have a detector or a camera. And what it records is, in first approximation, is basically 2D tomographic projection images of the molecules. So what you see here is just an artist concept. These are not, this is not a real micrograph. And so the 2D projection images that you see here are basically the integral in the direction of the beaming electrons of the electrostatic potential created by the molecule. The first task usually is to look at the micrograph and to choose, that is to pick particles, to select where they are. This is called particle picking. It's basically image segmentation. And then our task is to solve this inverse problem, to go from this very noisy tomographic projection images and to predict the 3D structure, to estimate what is the 3D structure. So it's very similar in a sense to medical imaging. Say a patient needs to go CT scan. But when a patient needs to go a CT scan, he or she are being instructed, do not move during the imaging process so that the viewing directions are completely known to the machine. And then the inversion is relatively simple, okay? It's a linear inverse problem. But with cryo-EM, we cannot give the molecules instructions. And basically, they just pick some random orientation that we do not know. And that's one major difference between the medical imaging problem and cryo-EM. The second difference is that, and I'll show you in experimental images in the next slide, the images are very, very noisy. That is, we're talking about signal-to-noise ratios that are much worse than what we have in medical imaging. And the reason for that is radiation damage. So as the electrons that are very highly energetic, say 300 kilo electron volt, go through the molecules, they basically break the chemical bonds, create ionization. So there is a maximum radiation damage. There is a maximum radiation dose allowed to apply before you're actually not looking at the molecules that you care about. So here are just samples of images from experimental data sets, one from my long-term collaborator, Fred Sigris at Yale, another from UCSF. And if you just look at the images, it's very hard even to see that there is a molecule there. All you see at first glance is just lots of noise. I don't know, like a TV set from the 80s that is not working properly. And it's amazing that we can actually get very high resolution reconstructions from such crappy images. And you ask yourself, okay, so how this is actually being done? Like, what's the magic here? And the answer is that we have lots of images. So in the first data set, like say 70,000 images, the second data set, nearly 100,000 images. So there is some kind of a clever averaging process going on that allows us to average out the noise and keep the signal. And this brings us closer to I'll have to tell you how this is being done mathematically. Now, around 2012, 2013, there was a really major advancement in the detector technology. I'll not go into the details, But this really gave a huge jump in the resolution that we can get using cryo-EM. So this is what this artistic picture tried to show you the improvement in resolution over the years from what you see here on the left, say the early 2000s, that you get very low resolution, just like blobs. And this gave cryo-EM the very unflattering nickname of blobology back then. All the way to, say, 2015, just after what is called the resolution revolution because of the new detector cameras. And nowadays, you can even reach like 1 angstrom resolution using cryo-EM for very rigid molecules. So you can see even at the atomic level. So due to this advancement, the resolution revolution, just a few years later, in 2017, the Nobel Prize in Chemistry was awarded to 3 of the pioneers of cryo-EM, Jacques Debussy, Joachim Frank, and Richard Anderson. And also, if you see just like the number of structures, let's say protein structures being determined by cryo-EM, you can see the exponential growth, okay? So this is like 2012, 2013, the resolution revolution. You see the yellow, the number of structures in the PDB, the protein data bank. And I say exponential growth because it's like in log scale that you see here, okay? And so it is very possible that in a few years, actually, cryo-EM will dominate X-ray crystallography in terms of the number of structures. You see a little dip at the end because the year is not ended yet, okay? I just downloaded this from the PDB a few days ago for the sake of this presentation. Now, it's not just the sheer number of proteins, but also the impact that it has on biology and even just global health, okay? So it's just one example that I like to show. So this is a paper in March 2020 in Science. And I think many of you recognize this structure because this is the spike protein of the coronavirus. And this was determined very early on in the pandemic. Actually, the structure was determined by cryo-EM, I think maybe a couple of months before March. So once you have the sequence of using cryo-EM, very quickly they're able to determine the structure. And this helped guide vaccine development and therapeutics. OK, Nobel Prize in Chemistry last year, now we're in the age of AI, was awarded for Baker, Hassabis, and Jumper, both for computational protein design, but also for protein structure prediction. So now that we have so many structures, both using X-ray crystallography and using cryo-EM, you can use machine learning AI to train on those structures and actually solve the protein folding problem. So you can ask me, OK, so now why cryo-EM? Why do we need it if you can now predict structures directly from the sequence? So it has many limitations. I don't want to get into it now. It's a completely different talk. But for example, one thing that they cannot do right now is actually give you like movies of proteins that are flexible. And this will go into the second half of my talk, how to do that using cryo-EM. OK, so now let's switch to math. So cryo-EM is, or single particle cryo-EM is actually an inverse problem. So I need to tell you what is the forward model before we solve the inverse problem. So the forward model is that after, say, particle peaking, we collect projection images, noisy projection images, that are simply the integral of phi. So phi is the 3D electrostatic potential of the molecule. So you integrate it in the z direction, so you end up with an image that only pixel xy. But you first need to account for the rotation, okay? This unknown element of the rotation group SO3. So that's how you obtain an image that depends on x and y, and you integrate out the z direction. There is also another element here that for the sake of simplicity for the talk, that I will avoid, that the CTF, the contrast transfer function of the microscope, described by HIs, that are, you can just assume that they are known. And also, perhaps also like imperfect centering of the images that I'll neglect for for simplicity today. And so what we obtain are n such noisy images. Again, phi is what we want to reconstruct, is the electrostatic potential of the molecule. And there are two inverse problems that we'll consider today. One is the basic reconstruction problem, when we assume that all images correspond to exactly the same structure phi. That is, we have a rigid molecule. And the second problem is what is called the so-called heterogeneity problem, is when we're dealing with a flexible molecule. Let's say I'm the molecule, okay? I can flex my arm, twist my head, and do all kinds of different. And so I can appear in different shapes, actually, different deformations. And then you want to estimate not just a single structure, 3D structure, but actually the entire distribution of possible structures and the density.
For these images, do you know a priori that you are looking at the same molecule?
You assume, yeah. A priori, you don't know anything, but yeah, some molecules are much more rigid than others. And so for those rigid molecules, we assume that this phi is the same for all the n images. And yeah, in the other problem, for more flexible or even composite heterogeneity, there will be a distribution. Maybe we'll talk about discrete heterogeneity when there are just a few dominant states, and also continuous heterogeneity of continuous flexible motions. By the way, feel free to ask me at any time. Okay, we have 60 minutes. If you have an urgent question, I don't see the point of waiting to the very, very end of the talk.
Okay, I've got a question.
Yeah, good.
Does HI depend on the angle?
It does not depend on the angle.
You had a subscript, right?
Yeah, it's a subscript, but it's the same HI for all. It's the same H for all molecules in the same micrograph. We use different defocus values. Okay, that's why it depends. Okay, but I don't want to go into too much into the physics. I know there are physicists here. I'm going to disappoint you. Okay. So the mathematics. So what I like about cryo-EM, that it's very rich in mathematics. Okay, so I was very lucky to get to work on it because it satisfied my mathematical curiosity, but also it's a problem that has a lot of scientific importance. So what kind of math will go into it? I will not cover everything today, but obviously statistical inference. We heard some statistics earlier today. Identifiability, we'll get into it also in my talk. Optimization, okay, how to solve for the 3D structure. Fourier analysis, you already mentioned Redon transform. Numerical analysis, dimension reduction, representation theory and algebra, information theory. And I put here machine learning with a question mark, okay? So as you can imagine, we're in the machine learning AI era. Everyone tries to apply machine learning on every problem that they see, okay? So I put a question mark here to say, okay, is it really useful in cryo-EM? And we'll address it later on. And you can imagine there is a lot of machine learning nowadays applied to cryo-EM. Okay, so there is a very, very basic theorem in tomography called the Fourier projection size theorem that if you don't remember anything from my talk today, please just remember this, okay? So what the slice theorem says, it says that it gives a really nice connection between the Fourier transform of the 3D molecule and the Fourier transform of the 2D projections of the molecule. So what is the connection? Okay, so if you have a 3D object, and now you can consider its 3D Fourier transform. On the other hand, you have a 2D projection image of that molecule, and you can consider its 2D Fourier transform. What's the connection between the two? So it turns out that the values of the 2D Fourier transform of a 2D projection image are nothing but the restriction of the 3D Fourier transform to a planar slice, okay, in the Fourier space or the reciprocal space that goes through the origin. Okay, so and that's a very important notion that plays a very important role, say, in medical imaging. because in medical imaging, we know the viewing directions. So if you take the 2D Fourier transform of projection images, you can now populate the 3D Fourier space with planes. And once you sample the Fourier space densely enough, you can then do Fourier inversion and go from the reciprocal space back to real space. And voila, you got your molecule back. Yeah, question?
Do you assume that the molecules are distributed uniformly, like every angle with the same probability? Or?
We'll get to it. Good question. So really, that's how you can do medical imaging. However, in cryo-EM, we get, as we said, we don't know the viewing directions. So we know that we sample the Fourier space on planes, but they're completely unorganized. And I cannot now do the inversion because I first need to figure out, OK, where to place my planes. So now identifiability, OK, you can ask me, OK, is this even possible? OK, if you don't know the viewing direction, maybe you can come up with different molecules that will all, of course, will all agree with the projection images that you see, OK? So here comes into play a really simple geometry that we know that any two planes in R3 will intersect at a line, OK, unless they are parallel to each other. So if we're dealing with clean images, what we can do, we can take the Fourier transform of those images. And because any two planes intersect at a line, there should be, say, a red line in image A and a red line in image I, where the values of the Fourier transform completely agree. And once you identify this common line of intersection, you know where the two planes intersect up to the angle between the two planes. And what do you do in order to figure out that angle? Well, you just add the third plane. So this was discovered more or less independently in the East and the West by Weinstein and Goncharov and by Marin van Heel. So three images and the common line between them allow to uniquely determine the relative rotations up to, of course, the global rotation of the entire molecule and also reflection. Okay, so the chirality or handedness cannot be determined by single particle cryo for the very simple reason that images of my right hand and images of my left hand are going to look exactly the same. Okay, so you won't be able to tell between my right hand and my left hand using single particle cryo. You need to do, let's say, a little bit of more like classical tomography. So these are clean images. So we know at least with clean images, we can reconstruct the 3D structure. We solved the identifiability question. However, what do we do with noisy images? Cryo images are very, very noisy, OK? So if the noise is not too bad, OK, then we can basically come up with better common line approaches. And I've been involved, and my student, with lots of, in this direction, using semi-definite programming approaches that generalize, or like, say, the SDP approximation to problem like in max-cut, synchronization of rotations, and so on. And you can also try to improve the SNR of the images by denoising, say, averaging images that you believe were taking in similar viewing directions by using graph methods like diffusion maps and coming up with invariant representation of the images and so on. And all of this really, really helps, OK? And we've done lots of ab initio reconstruction using this. But at some point, I asked myself, OK, we cannot apply it to very noisy data. Is it because I'm not smart enough? My algorithms are just not good enough? Or is it because there is some fundamental limit here that at low SNR, I just cannot estimate rotations? And the issue is really that there is no need to come up with very, very sophisticated algorithm because estimation of rotation is really impossible at very low SNR because even an oracle will not be able to estimate rotation at very low SNR. And the reason being, so imagine an oracle that knows the 3D structure, OK? I don't know the 3D structure. So the oracle should be in much better position to be able to estimate rotation if they know the 3D structure. So what the oracle would do, it will just generate clean 2D projections of the molecule and then try to match the noisy experimental images with those clean projection images. But because the images are so noisy, any metric that the oracle would use, okay, will give you like very huge fluctuations. And because of the noise in the images, and the estimation of rotation would just be very poor, okay? So if the oracle cannot do it, essentially my algorithms will not be able to do it. And then there is another question that follows. Can we determine the structure in cases that the SNR is so bad that we cannot estimate rotations? Okay, so structural biologists, they don't care about rotations, okay? They want to know the structure. And so as a mathematician, the first thing that I try to do is the way I've been taught all my life, okay? How to solve a problem? Well, first try to bring it to a point that you do know how to solve. So I did know how to solve the medical imaging problem, given that I know the rotations, okay? But then I got stuck, okay? Maybe there is a shortcut here that we can solve for the 3D structure without solving for the rotations. So the fact that we cannot solve rotation doesn't mean that we cannot solve for the 3D structure. So the answer is yes, okay. Otherwise, at least this first half of the talk would be over. And the way this is being done in most software packages like Relion and CryoSpark and others is using what is called marginalized maximum likelihood. So the parameter of interest is the 3D structure, but all the other parameters are called nuisance parameters or latent variables that you basically marginalize over. So the rotations here are actually nuisance parameters that you basically marginalize or integrate over. And you can view it basically as missing data, those rotations. And this falls very nicely into, when you try to do maximum likelihood, to use the EM algorithm. And it has just two steps, the E step and the M step. The E step is just what the oracle tried to do before. Basically, given a guess for the 3D structure, try to match the noisy projection images with the clean templates. But now, instead of doing hard assignment, just do it in a software and assign probabilities or weights. And the M step is the medical imaging problem, okay, the reconstruction. Given that you know the rotations or even just probabilities, now do the tomographic reconstruction. The problem with EM is that it's quite slow. You're not guaranteed that it will converge to the global solution, the actual maximum likelihood. And in practice, it fails for small molecules at low SNR. And then you ask, OK, so then I said to myself, OK, let's try. It's very difficult to analyze what EM is doing. So like even answering some very basic question as a mathematician, how many noisy images do we need to determine a 3D structure as a function of the SNR? Is there a threshold below which we cannot do the reconstruction as suggested by the failure at low SNR? Or maybe just that we need maybe exponential number of more images, or what's going on here? So for that, we consider even a simpler estimation method, like in Statistics 101. So before maximum likelihood by Fisher there was the method of moments by Pearson. So let's try the method of moments. Why is it attractive here in cryo-EM? Because all you need is to compute moments. You just need like one pass over the data. Okay, so it also has some computational merit, not just that it will be easier for us to analyze. So what is the method of moments, okay? So the method of moments, you first compute, let's say, the first moment. You take all the noisy images, and you'll compute the sample mean, okay? M1, this will be the first moment. And then the second moment, what you'll do? Well, you'll take pixel xy, y1, pixel x2, y2, you multiply them both, and now you average across all the images. Okay, so this will be now 4-dimensional in a sense. Okay, you have 2 pixels. Third order moment, now it will be like a third way tensor. Okay, you multiply 3 pixel values, and now you get this third order moment, and so on. Why empty? They will become bigger and bigger and bigger and bigger.
Yeah, but spaces are bigger, but few parts are empty.
No. It will be full dense moments. Very messy, unpleasant to work with. Yeah, so the higher order the moment, it becomes more and more, I mean, you need more storage, for example. you need more compute time to compute them, okay? So, but now we're just doing it on paper, and the question is, can we estimate, if I give you the moments, okay, why it's nice to work with moments? Because noise average out, okay, in the first moment. Noise in the second moment, I know just what will be the contribution of the noise, and I can eliminate it. The same with the third moment, okay? So I can really estimate, with enough data, I can estimate actually the clean moments from very noisy images. So the question is, can I estimate the 3D structure from the moments? Clearly, I cannot do it from the first moment, okay? The first moment is just a 2D image. I cannot reconstruct a 3D structure from a 2D image. But maybe the second moment is enough. If not, maybe I need to go to third moment. Okay, who knows, okay? We're good. Okay, so turns out that the first moment is not even 2D because of in-plane rotational symmetry. Every image can appear in all possible in-plane rotations. So it's effectively one-dimensional. For the same reason, the second moment is not four-dimensional, it's just three-dimensional. And then you pause for a second, okay? You say, oh, I need to reconstruct a 3D volume, okay, a 3D structure. The second moment is effectively three-dimensional. Maybe we're lucky, okay? And we have the same number of parameters and the same number of variables. Maybe we're lucky and we can invert the relationship and be done. So yeah, so is it enough just to consider the first and second moment and get the 3D structure? So it turns out that this was considered, actually the year I was born, by Zvi Kam from the Weizmann Institute in Israel. And okay, so what was Kam's idea was exactly that, okay, to look at the second order moment. But he considered for the case, you asked the question, right? What do I assume about the distribution of rotations? Is it uniform? Is it not uniform? So Kam assumed uniform distribution of rotations. In practice, it's typically not uniform. Okay, there is what is called the air-water interface. Molecules prefer to orient themselves in a certain way, but so it's typically not uniform, but yeah, but Kam did it for uniform distribution. And again, because of the slice theorem, okay, let's see how much time I have. Okay, we're good in time. So because of the slice theorem, there is a really nice thing that you can tell about the second moment if you consider it in the Fourier domain. Okay, so in the Fourier domain, we know that if we take the Fourier transform of projection images, we know that they correspond to slices. So now take two frequencies, and you're going to multiply them and basically average over all the images. So when you do that, every image corresponds to a different slice. What you're going to do is really to integrate over the rotation group SO3. What are you going to integrate? Basically, the product of the Fourier transform of the molecule times itself. And now you do integration against the Haar measure over SO3. What is this integral of the product? It's just the autocorrelation of the Fourier transform of the molecule with itself over SO3. So the second moment is equivalent to knowing the autocorrelation function of the Fourier transform of the molecule. I think most of you know that, say, if you consider the autocorrelation of a one-dimensional function, a function of just a single variable, you cannot reconstruct the function from its autocorrelation. Because if you take the Fourier transform of the autocorrelation, you'll just get what's called the power spectrum, the magnitude squared of the Fourier transform. And so this leads to the very famous phase retrieval problem, that you get the magnitude of the Fourier transform, but not the phases. The same thing happens here. The right language to represent the molecule now is using spherical harmonics and some radial basis functions. And turns out that from the data, okay, I'll not show you the derivation, but from the data you can get these CL matrices that you can compute from the data. K1 and K2 are just radial frequencies. And they will relate to those unknown functions, okay? So you can get some information about these functions, okay? The radial components of the spherical that come with the spherical harmonics. Or in matrix notation, you can write it as CL equals to AL times AL complex conjugate transpose, meaning that you see now that from CL, you can almost take the square root, okay? You'll do Cholesky decomposition. You'll get the AL, but the Cholesky decomposition is not unique, okay? You can multiply this AL by any unitary matrix. So again, just like in phase retrieval, we don't get the phase, okay, this e to the I phi. Here we miss unitary matrices, okay, the same analog of the phase retrieval problem, but now with unitary matrices that are missing. Okay, so this shows you that in the case of uniform distribution of unit directions, the second moment is insufficient. So already Kamm saw that, okay, maybe we can add higher order moments, but he realized, okay, the moments are very high dimension, or maybe we'll use just a slice of the third moment, a slice of the fourth moment. And numerically, at least he saw uniqueness at very, very low resolution, okay, that he worked with. Okay, later on, okay, so this takes us much more recently. So this is work of my former student, Afonso Bandera, with his collaborators. And here I really need to give a shout out to Asaf for leading the A&G collaborator that was here, funded by the Simon Foundation. So Joe Khalil was a postdoc working with me at Princeton, but he was really an A&G postdoc. And he worked with all this group of people that came for the A&G meetings. And then he came up with actually a proof that the third order moment guarantees uniqueness, okay? So that settled it. Before, in collaboration with Emmanuel Abe, who was at the time at Princeton, and my former student, Joao Pereira, that was really his PhD dissertation. So Emmanuel is like a world expert in information theory, and we're able to show that this is actually information theoretic optimal, okay? So the fact that you need to go to third order moment, and when you multiply 3 pixels together, and each of them has a variance of sigma squared, at the high noise regime, this means that now the variance of elements of the third order moment scale, I mean, they have noise at variance of like sigma to the 6, okay, because he multiplies 3 terms of sigma squared together. So the number of images that you need, now you see scale as sigma to the 6, or 1 over SNR cubed. This is a vast contrast with classical statistical estimation problem, where usually the sample complexity, the number of images or samples that you need, scales 1 over the SNR. Okay, if I'll ask you, okay, estimate the mean of a Gaussian with variance sigma squared, you say, okay, I'll need an order of sigma squared samples. Here you see that because we don't know the rotation, these latent variables that are missing here, the sample complexity jumps to like sigma to the 6. But there is no threshold, okay, that we can say, okay, below which it's impossible to do reconstruction. But it's annoying that we have to work with third order moment, okay? Computations are terrible, okay? We'll need more images. It's much higher dimensionality. We don't have all these nice tools from high dimensional statistics to do eigenvalue shrinkage and optimal estimation of covariance matrices. So it's either, can we do better, okay? Can we somehow avoid third order moments? Yeah, question?
This is a question kind of from the physicist. So there is presumably some length scale in the noise, right? So there is some size of the pixel that is noise, and there is the size of the molecule. And the size of the molecule exceeds this, and presumably it's not really an SNR, but it's like the ratio of the scales that matters, right?
Yeah, so this goes more into the resolution of like, right, exactly. Yeah, maybe we can discuss this later. Okay. Okay. So one way to avoid third order moment is to consider the case of non-uniform distribution. Okay, going back to your question, and remarkably, what we were able to show that in the case of non-uniform distribution of unit direction, even if you don't know the distribution, it is possible, at least on paper, like to get uniqueness with only the second order moment. In practice, we're only able to get very, very low resolution. But somehow, when you have non-uniform distribution, it breaks the symmetry. Okay, so now spherical harmonics of all orders talk to each other through this non-uniform distribution. Okay, you get coupling. So you can basically write the second order moment, what it provides as information, basically as polynomial equations that are quadratic in the in the 3D structure that you try to recover, and linear in this unknown distribution. And now there is going to be coupling between different spherical harmonic orders. So schematically, this is like a dream that is not yet materialized. But basically, second order moment will just be do PCA for the cryo-EM images, and then from the PCA, from the eigen images and the eigenvalues to predict the 3D structure. But just doing nonlinear optimization to solve these quadratic equations. For now, we can just do it at low resolution. Another approach is to exploit sparsity. Okay, so Ingrid is sitting here. So this is a lucky coincidence. But basically, we consider two different types of sparsity. One is basically a sparsity model of a bag of atoms model. That basically the molecule is just made of atoms, okay? So I don't know, there are 10,000 atoms, but you don't need 100 million voxels to describe the 3D structure. And you can even make them not just like delta spikes, but a mixture of Gaussians, okay? They are just a little blobby. Another type of sparsity is sparsity just in the wavelet domain, okay? To say, okay, that the molecule has very sharp decay of the size of the wavelet coefficients. In this case, we actually have a theorem that says that, okay, second order moment suffices, okay? In this case, we don't have a theorem, we just have an algorithm that seems to work well, okay? And it's based on actually algorithms that people use in phase retrieval, okay? Like Douglas-Rutherford or what is called like an RR, reflect, and so on, algorithms. So that's for sparsity that, again, you can just do with the second order moment. Another approach is just to compress the third order moment, okay? And here I actually show you, okay, result with lots of simulated images. So we used 2 million projection images, but they are very, very noisy, okay? The SNR is 0.01. And with this simulative data, that was the ground truth structure. That just a low resolution version of it when we projected it to only the first 10 spherical harmonics, okay? Spherical harmonics up to order 10. And this was the reconstruction from the compressed third order moment. This is another reconstruction from the third order from the compressed moment. What is the difference between the two? Okay. It's the way we do the optimization. Okay, so that's something that I shoved out in the rug until now. But you can ask yourself, okay, when you have the first order moment, second order moment, third order moment, how do you now optimize and find the underlying 3D structure? So what we did here is we first matched the first order moment. After matching the first order moment, we matched the second order moment. And then we match the third order moment. We applied it in stages, and here we try to solve for everything at once. And you can see this is doing much better, and I'll explain why. But this will come in a few slides. Okay, another thing that we are even continuing developing now is basically to leverage on the amazing improvement that we have from AlphaFold and AlphaFold 2, that basically can actually predict a really good ab initio model. And then you can just correct it a little bit with the second order moment. Okay, and then you just need second order moment. You don't need third order moment for that. And finally, you can actually use multiple data sets of the same molecule, but in the sample preparation, somehow guide the molecule to take different distributions of viewing directions. So for example, there are ways to make the molecule take more of uniform distribution. I will not go into it now, but then you can take those two data sets, compute second order moment from each one of them separately, and then solve for the 3D structure. Okay, so before we conclude this part of the talk, I want to say a few words going back to the optimization that I talked about, but also some take-home messages beyond cryo-EM. So I told you about maximum likelihood that everyone uses, okay, as the workhorse in Rely-On and CryoSpark, and I told you about the method of moments. Is there like any connection between the two? So it turns out that there is, and so that's something that we realized for cryo-EM, and then there are like, so this is like in Joao's PhD dissertation with me and with Emmanuel, but then many other smart people did it for different kind of problems. And in all these problems, what you realize is that if you consider the log likelihood function, and you consider its Taylor expansion, or what is the parameter for the Taylor expansion, the small parameter is the SNR. Okay, so when you're dealing with very high noise regime, the SNR is very low, okay, and you can consider it as a small parameter. This will be like your epsilon in the Taylor expansion. And in that case, you can ask, okay, what are the terms of the Taylor expansion series? Turns out that the terms of the Taylor expansion series of the log likelihood function are nothing but the moments. So the first moment will be the term of the SNR, the second order moment will be SNR squared, and so on and so forth. So what does it tell you? It tells you that, well, we know that maximum likelihood is the efficient way for parameter estimation. So really, when you want to optimize with your moments, you want to scale them with the SNR to the right power and give much more weight to the first moment, compare asymptotically much larger weight to the first moment compared to the second moment, and then to the third moment, and so on. So, and that's why the moment matching technique that I mentioned before works so well compared to, say, just taking all the moments together and optimizing at once. So we also did it recently. We applied a similar technique to just Gaussian mixture modeling, where you know that this is like the, I don't know, like when you teach EM in class is probably the first example that you show for EM, when you do Gaussian, how to use EM for Gaussian mixture modeling. But we used method of moments for this problem of Gaussian mixture modeling, but now taking into account this small parameter and doing it in a smart way, and it seems to be working like even better than EM. So, and even correcting some of the other issues with the method of moment that people notice in econometrics and other literature. Okay, so now I'm going to switch gears and talk about flexible molecules, okay? And okay, so this was the dynamic direction for cryo-EM, okay, where you see here the molecules that can be in like open or closed, okay, molecules that can bend and twist, and there is no rigidity anymore. How to actually now not reconstruct a single molecule, but the whole entire movie, okay, or give you a video of what the molecule is doing. So this was one of the methods to watch in 2022 by the journal Nature Methods. And let me switch here. It's much easier to show movies in PowerPoint than in PDF. So let's switch. Okay, so that's the heterogeneity problem. So there are two types of heterogeneity. One is discrete heterogeneity, where a molecule just picks some, say, a few, say, metastable states. And there is what is called continuous heterogeneity, when something will just move continuously. Some part of the molecule will move or rotate or flex or whatever. And there is, you can see, I listed just a few of the methods that were developed recently. There is a lot of activity in this area in terms of method developments. Many of these methods are based off deep neural nets. The most successful one and the most popular nowadays is what's called CryoDragon, developed by Ellen Zhong, who is now computer science at Princeton. And all these methods actually operate in 3 stages, okay? So there are 3 steps. So the first step is usually you get the noisy projection images. Okay, now you assume that you've already know the rotations. Okay, these are usually much larger molecules, so unlike the first part of my talk, you can actually do estimate rotations. And so usually you know rotations, but then the question is, okay, we have some, again, the latent space, but now this latent space corresponds to the latent conformational space, okay? So this space will correspond to every point here in this conformational space will correspond to different conformation of the molecule. So then step one will be to embed the noisy images in a common space, this common latent conformational space. Then in step two, for every point in the latent space, you want to reconstruct the 3D structure. And then in step three, you want to do motion estimation. So say I give you 2 points, 2 states. Can you figure out what is the transition path from this point to this point? Is it here, this path, or that path? Okay. And then, given the path that you predicted, then you can show the movie, the motion. OK, so how is it done, let's say, using a deep neural net? So this is a CryoDragon. It's basically a variational autoencoder architecture. So the encoder is doing for you step one of the embedding. The decoder is doing for you step two of getting the 3D structure, the reconstruction. There is no really step three of motion estimation. You can do something crude of like using some graph methods. But just to give you an idea how this is being done using deep neural nets that are quite successful, okay, I have to admit. So alternatively, okay, so this is the work that basically Mark did most of the heavy lifting in this work, okay? So he started working with me as a postdoc at Princeton. Now he's an assistant professor in our math department. And he really did most of the work here. We operate differently, okay? So we call the method, okay, depending on who pronounces it. I usually pronounce it recover. Other people pronounce it recover, okay, based on your preference. But step one is just to embed using principal component analysis. You cannot apply PCA directly. You need to apply PCA to the 3D structures, but all you obtain are 2D images, okay? So you cannot just apply PCA directly. But okay, so some variation of or clever extension of PCA to get the embedding. Then the reconstruction, we do it using kernel regression. Okay, so again, very classical statistical analysis. And step three, we just estimate the densities. And we know from Boltzmann statistics that how to relate the density with and free energy with the potential, and then find what is the transition path using by solving a PDE. Okay, so that's what we do, and let me show you some comparisons. Okay, so these are for actually experimental data. So what is good about cryo-EM that, I don't know, unlike other maybe fields in biology, people actually share the data, okay? After they publish, okay, so they publish in Nature, Science, and so on, but after they publish, they are willing to share the data with the method developers like ourselves. And so Empire is a public repository for electron microscopy data. So you can see that the embeddings look relatively the same. On the left, you see the CryoDragon one. On the right, you see what we get with Recover. Here I show you state A, okay? And okay, now I'll show you just the 3D structures that you obtain. So your eye is not very trained to look at of such structure, but I hope you can see that something is missing here that you see here. Okay, and also when it was twisting and turning, okay, you can see that this is like it's much more spiky, and there are some, okay, like I don't know, you can see here much better maybe than what you can see here, and so on. Okay, so just to give you some idea first, okay, here is another data set. Okay, this is the same data set but different state, now state B. And I'll let it, oops, I did it too fast. Okay, I'll let it twist and turn, okay. Okay, and I'll help you to zoom in, okay. So for example, here, if you look at the red part, I hope you can see differences in the resolution, and you can see like really the helical structure, or in the green part. So, okay, but this is like maybe just one example, okay? And I'll show you later a more comprehensive study. There is also bonus in runtime, okay? So since all we do is, and yeah, we do have like 10 minutes. So I can tell you a bit how we compute how we do the PCA and so on. These are like numerical linear algebra, okay? So on a single GPU, it takes like somewhere between, I don't know, 10 to 20 times faster to do the steps of recover compared to CryoDragon. Okay, so let me now switch back here. Yeah, so like I mentioned, it would be like really nice if there was some, I don't know, benchmark that, independent benchmark that compare all the different methods. And luckily, Ellen and Princeton and her students, they did such a benchmark. So they compared CryoDragon and other heterogeneity analysis methods on, I think, like 5 different benchmark data sets. These are synthetic data sets, so they know everything about the data sets. And usually in those benchmarks, they show you in bold the method that is doing the best. So here, the numbers correspond to some measure of the resolution, and the highest number is better. And then one day, Mark and I receive an email from Ellen saying, like, you know, like, recovery is doing like amazingly well. What is like the secret? What is the secret ingredient? Okay, and you can see, okay, that in 4 out of the 5 benchmarks, it's doing better than all the other methods. Even in the one data set that it's not, it's really, I think, okay. With a different parameter choice, we could have done better. Okay, so. And then my answer to Ellen is that we actually understand all the steps that we're doing, okay? And we can even give guarantees for everyone. It's actually CryoDragon and deep neural net that we don't really understand what's going on. The fact that there are so many successes of neural nets in other fields and you now expect it to work so well in this application doesn't mean that it should, okay? And it should outperform everything else, okay? So. And it's not only in terms of the resolution. I want to show like the embeddings that you get, okay? So here is like, again, from their paper, an example of conformation heterogeneity that just one part of the molecule is rotating 360 degrees. So the embedding should just look like a closed curve. And you can see that closed curve really well here. And the color ordering is very nice, what Recover estimates. And you can see that the other methods, some of them can even give you the impression that there is some 2D variability going on here, where there is not, okay? So it's not just the resolution, but also if you want to actually understand what the molecule is doing, it's giving you a better idea of what's going on. Yeah, question?
So if the states of the molecule are very distinct rather than rotation of one dimension, this is like really breathing, you presumably need to cross the individual instances, individual projections somehow, or the reconstruct volumes.
Right, so I'll tell you how we do the reconstruction, maybe very briefly, okay, because we have 7 minutes. Okay, so yeah, so like we said, there are 3 steps, okay? PCA for the embedding, then kernel regression for reconstruction, and density estimation and computing transition path for producing the videos. And I just want to tell you maybe how we do the PCA step. By the way, if you want to play with the code like you asked me before, here is the link. Okay, so how do we do PCA? And that will be the final mathematical nugget for today. And I'm closing again with the Fourier projection size theorem, okay? So you want to estimate the covariance matrix of the 3D structures directly from the 2D projection images. You know that every projection image, now you know its rotation corresponds to a slice. So if you just choose 2 frequencies on the image plane, you know they correspond to 2 frequencies in 3D. So basically, by looking at the covariance of all the images that correspond to the same viewing direction, let's say, you can basically estimate the covariance between any 2 frequencies in 3D. And in that way, you can actually populate the covariance matrix of the 3D structures. You see already that we're very lucky that we're in 3D, okay? That we get 2D projection images of 3D objects. If I were to do this in let's say, if we're 2D objects and 1D line projections, I would not be able to estimate the covariance matrix, okay? Because now if I have only lines, okay, every 2 frequency will be collinear, okay? I cannot now estimate the entire covariance matrix. But the fact that we are in 3D and we get 2D projections is very lucky here. It also shows you the limitation that I can estimate the covariance matrix, but I won't be able to estimate the full, let's say, third-order moment of the distribution, because I can only estimate third-order moment of like frequencies that are coplanar. I cannot take any 3 frequencies in general position. So you see why the heterogeneity problem is actually much harder, okay? In general, I cannot solve for the entire moments of this distribution. But that's what we do, okay? So we can estimate the covariance matrix. There is obviously a computational issue that it's a huge matrix, okay? If a volume is 100 by 100 by 100 voxels, okay, million voxels, the covariance will be a million by million, okay? It's a huge matrix. So the way we do it is we leverage of some of the recent advancements in randomized numerical linear algebra. And instead of estimating the entire covariance matrix, we just estimate a few columns of the covariance matrix, knowing that this matrix is going to be low rank, and just using the SVD of the columns that we computed. And that's what Recover is doing. Okay, so everything that I talked about today you can also find in Aspire. This is our toolbox for computational methods and algorithm for signal particle reconstruction. It's in Python. It's open source. You can play with it, make projections, add noise, whatever you want to do. And I just want to summarize with those 3 points. So first of all, cryo-EM is transforming the field of structural biology. I hope I was able to convince you that in the first part of the talk. Reconstruction is a very rich mathematical problem. I haven't even touched all of it, but I kind of joke with people that want me to tell them about cryo-EM that whatever math you're interested about, I'm kind of positive I can find a subproblem in cryo-EM that will suit you, okay, and that you can work on. And the third point is that don't give up on classical applied math and statistical analysis that everyone tells you, oh, I can do your problem with machine learning and AI, and have you tried it on your problem? It's going to do better, and so on. So if you're willing to invest, so I would give them that if you want to get decent results, maybe not the best result, but relatively quickly, using the current software tools in machine learning, you can relatively quickly get very decent results, okay? And if that's all you care about, then great, okay? But if you care more about your problem, especially in the sciences, I still think there is no replacement for a very careful classical applied math and statistics. And even for a problem like cryo heterogeneity, that seems ideal, okay? Like it has all the hallmarks that needed, like for machine learning. You have massive data sets, high-dimensional data set, and intricate nonlinear structure, and yet we can do better with classical applied math and statistics. Okay, so with that, I would just like to thank you and all the funding agencies, and especially the SIAM Foundation, that I wouldn't be here without it, with all the funding for the Math+X Investigator Award. So thank you very much.